journey. Alright. So as you see now, yesterday we were discussing this. So types of motion involving rotation. I think now it is clear. So some students had difficulty in rotation because we have usually used the word rotation for this, and for something moving like this we have used the word revolving. Okay, we are not going to use this word revolving here. We are going to say about this point it is rotating. Okay. So therefore the confusion is allayed. So rotation about the fixed axis. Yesterday we have discussed the ceiling fan. So you can see that there is an imaginary line drawn here, an imaginary line drawn here. Okay, and about this line, if you take any point on this wings or on this disc, okay, the each of the points are performing circular motion, and the plane in which each of the particle is making circular motion are all parallel to one another, and it is perpendicular to this line, and each of the particle is moving in a circle, and the center of each of the circle is along the axis of it. So therefore axis has all these conditions. And similarly, when you open the door, this point of the door where the hinges are put becomes the axis of the door. Right? And when the door is moving, every particle on this door is making rotational motion. Okay. Now there are some more typical cases, because now you see why we are doing this exercise is because now we are going to understand the something very real, because now you see so far a particle is in motion. There is no particle, but we have made a concept of particle and we have understood quite a bit of dynamics. Okay, so now we are going into body, right? And now when I throw a body, when I throw a ball or shuttlecock or something, now its motion is it is translating, it is rotating, and it's combination of all of them. So now we need to create math models for all of them. Okay, and therefore we are creating some concepts here, and we will soon be able to connect these concepts and come closer to the reality. I mean, closer to representing the realities. Okay, now you can see here that you can see this body here, right? Now you can see. Now what is this? This is that is it can oscillate about this point P.
Yes.
Now in this context, I will say this body is rotating about this point P.
Yes.
Got it? Now what is this? In this case, what is this body? This is a compound pendulum. A simple pendulum was what? One pivot point, you had a thread, and then you had a ball. Point mass. But now this becomes compound, and you are going to find the period of oscillation of this compound. I will give you the mass of this, right? I will give you the mass of this and other geometrical values, and then you will be able to find the frequency and the time period of oscillation. Okay, so here you see, we see it is rotational because PB is not parallel to PB dash. PB dash is not parallel to PB. You see here, that is yesterday's discussion. We have created a line, and we have drawn an arbitrary line, and this arbitrary line, okay, is making an angle. That is, we have created this arbitrary line, and we have also created an arbitrary we have created a reference direction. Assume that the reference direction is passing through PB.
Yes, sir.
Okay, now as this body is moving, this reference line now shifts from PB to PB dash, and it is making an angle, and the angle is changing, and therefore we say this body is rotating with respect to this point P.
Yes.
There is no confusion. There is no confusion whatsoever. This is a body, right? This is a body. Now if you take the particles of this body, if you take any particle of this body, okay, or any two particles of this body, okay, what will those any two particles of the body do? Curvilinear translation.
Yes.
Curvilinear translation. Got it? Any two particles, please appreciate it. And now you can see here that a ball is rolling without slipping. Okay. So you can see here that again we have drawn an arbitrary line CD, and you can see that there is a vector drawn here. Okay. So this vector here is indicating what? It is indicating that this object is moving to the right, or it is has a velocity vector to the right. So there is, that means this body is translating, and about this point C, this body is rotating. You can see that this arrow is there. So a ball rolling is a combination of both rotational motion as well as translatory motion. And see, we will create the models such that we will separately consider the conditions for rotation. We will separately consider the conditions for translatory motion, and we will create math models for both, and then we will combine both and get the complex motion.
Yes, sir.
And not only that, now this is as far as the body is concerned. Now if I take any particle on this body, now what is the type of motion that a particle of this body will make? See, if you take this particle will go down.
Only rotation.
Listen, how only rotation motion? If you take this particle on the top, this particle will come down here. See here, it will come down here, and again it will go up like this. It will touch the ground and then keep going. Okay. So all those things we will understand. And this is one more thing which all of us love to do. This is a shuttlecock in flight in midair. So you can see that the shuttlecock is continuously moving. It is translating. You can see from this chord to this chord. So you can see this arrow. It is the velocity vector, translation velocity vector. And at the same time, an arbitrary line drawn here. It is rotating. So it is again a case of combination of these two. Okay. Right. So I've already discussed this issue. Okay. Now, yesterday we had a brief discussion about axis of rotation. Very important. Imaginary line perpendicular to the plane of the circular paths of the particles of rigid body in rotation and containing the centers of all the circle paths is known as axis of rotation. It is not necessary that the axis of rotation pass through the body. Tenicoid ring. If you don't know tenicoid ring, you should ask me. Right? Consider system shown in the figure where the block is fixed on see here, there is a block fixed on a rotating disc. The axis of rotation passes through the center of the disc but not through the top.
Yes.
Right. Now another diagram which will bring out some more aspects here. Okay. Let us consider a rigid body of arbitrary shape rotating. So you can see here a rigid body of arbitrary shape is moving. All the particles are not on the axis of rotation, moving circular paths. All the circular paths are parallel to the plane. I suppose you can now appreciate. I have taken one particle here, another particle here, and this circle that you see is perpendicular to this dotted line. What is this dotted line? Axis. Now in this case, this axis is passing through the body, and so it is getting connected with some particles of the body, and this set of particles of the body through which the axis is passing, axis is in imaginary line, it is at rest.
Yes.
While all other particles of this body are in circular motion with its center on this axis. And you can now you can see that this particle is rotating in along this circle, and if you this circle itself, if you consider the area bound by this or the region bound by it is a plane. So you can see this plane and this plane are perpendicular to the axis and parallel to each other.
Yes, sir.
And so it is shown here with this one here, indicating that this is rotating, and
Yes.
PQ becomes the axis of rotation. Okay, right. Now remember, axis of rotation need not always be the geometric center or center of gravity or center of mass. Axis of rotation can be anywhere. I suppose you can visualize that.
Yes, sir.
Yes.
Huh?
Yes, sir.
So here you see, I can make it visualizing. So here you see, I can constrain it here. So between my two fingers, whatever points are there, those particles are there, though they are constrained from moving. So the axis is passing between my two fingers and therefore it is rotating about this. Now I can move my finger here and cause it like this. Okay?
Yes, sir.
Yes. So axis is something which I can also choose it like this and make it rotate. So in fact, you know how many axes I can pass? Infinite. Okay. All the particles of the body. Now these are some important abstracts here. All the particles of the body cover same angular displacement in the same time interval. Therefore, all of them move with the same angular velocity and angular acceleration. Okay. Now, if you take this body here, so you can take any particle here, this particle or this particle. So this has rotated. That means each particle has got same angular displacement. See, you appreciate? Now, if you say my hand, so from the tip to this point, you can mark points here 1, 2, 3, 4, 5, 6, 7, 8, and 100 points here. 100 particles. Now, if I move my hand, see the first particle here to the tip of my finger has gone through theta. The second particle here, it has also gone through theta.
Yes, sir.
Every particle has gone, so the angular displacement of each of the particle is same.
Same, yes.
But the distance moved by this particle, the tip, is more. The distance moved by this is less.
Yes, sir.
So,
Yes,
so therefore, theta by t is common to all the particles.
Yes.
But
Yes.
the distance moved, dl by t is not constant.
Okay, yes.
So
Yes.
therefore, angular velocity, angular acceleration is same for all the particles, but linear velocities and linear accelerations are different.
Yes.
So I hope these differences are clear.
Yes,
Right?
yes.
Good. Now, particles moving in circular of different radii move with different speed and different magnitudes of linear acceleration. Further, no two particles in the same plane perpendicular to the axis of rotation have same velocity and acceleration values. No two particles in the same plane perpendicular to the axis of rotation have same velocity and acceleration. They say same
Yes.
velocity means linear velocity and linear acceleration.
Acceleration.
Okay. All the particles on a line parallel to the axis of rotation move in circular paths of same radius, therefore have same velocity and acceleration vectors. Okay. Did you understand this point?
Yes, sir.
Good. Anybody did not understand that point? Everybody understood?
Yes, sir.
Great. Okay, anyway, some of you are keeping quiet. So, you didn't say yes. So, therefore, I have to write it. So, now you see, this is say there is one particle here. It is moving in a circle about this axis. And there is, that is, I will take this as a solid disk. I will take this as a solid disk and I am choosing this particle. I will take another solid disk. That is, this is the body. This whole thing is a body. Now I am going to draw a line parallel. So again here there are particles, everywhere there are particles. So I am drawing a line parallel to the axis of rotation. This is the axis of rotation. I am drawing this line parallel to that, and now along this line this particle is intersecting and this particle is intersecting. Understand? So this particle is moving in this circle, same circle as this. Okay.
Yes.
Now, whatever is the angular velocity and angular acceleration of this, the same will be for this.
Even linear velocity.
Yes, obviously.
That was the point.
Obviously, the linear velocity and linear acceleration will be. So, whatever is the condition for this, the same condition will be.
Yes,
Yes,
sir.
sir.
Except that if you take this plane as the z is equal to 0, then this will be at some point z1, this will be at some point z2.
Yes.
This is z is equal to 0 plane. So this is z axis. If you take it, then this is at z, this is equal to z1. So all conditions will be same. See, these are all very, very important abstractions because this will help us to create the right model and tackle the numericals very, very effectively and efficiently.
Yes, sir.
Huh. So now consider any two particles in a plane perpendicular to the rotational axis. Every such particle of the rigid body in rotation moves in circular related to one another. The radius of circular paths equal to the distance between the particles. In addition, angular velocity equals to that of the rotational. That is precisely what I have explained. Okay. Now another way to look at it. Another example of fixed axis rotation is a spherical globe rotating about a fixed axis about any diameter. So if you take a globe, now the thing is, about any diameter. So there is an axis is being passed through any of the diameters of the globe, and you can see every particle will execute circular motion. This is another typical diagram just to show that the radiuses are different. Okay. Now some. Yes, please.
Can you please go? So I said every such particle on a rigid body in rotational motion moves on circular path relative to another one.
Relative to
Another one.
Okay. So see, I wanted to take up that issue later on, but anyway, you have taken it up. Now, well, that's a nice thing. Now you see here, this particle is rotating, right? This particle is rotating. Now you take another particle. Okay. Now if you draw, this is another particle. This particle is P1. This particle is P2. Now if you draw a line from this particle to this particle, and if this is rotating, so you will see that this line is also changing. That is, if you take this as the reference line, so these two particles are moving, means this line is changing now.
Yes.
So therefore, see what we had built the theory. That is, a particle is rotating. The particle is rotating. Then for the condition we said, you draw any arbitrary line, and if it is making angle, if the angle is changing, then we say it is rotating. So this particle and this particle, if you see, so this will change its orientation. Right? And this will also change, provided both of them are diametrical or otherwise also. That is, if you join any 2 points, that line will be moving.
Yes.
So that will give us an idea of rotational motion. See, okay, now Srijan, you do like this. I will not take this particle. I will take this point P. I will take this point. Okay, then I will take this particle. Here this particle, with respect to this point, at some time T1, it is this line. At some time T2, this is the line. At some time T3, this is the line. So this angle is changing. You remember the theory that we had built?
Yes.
So with respect, and so that means now here you see with respect to this point, this is rotating. So therefore now, if you take a body in rotation, every particle is rotating relative to some other particle.
Yes. Okay. So but the other particle can also be in rotation.
It can be in rotation. That's what I said. You take a point there. If you take it as a point, then other particle is rotating with respect to this. See, now if you see, you understand here, the reference is something that I am fixing. I am fixing the reference as this particle, man. And I did not say that reference should be fixed.
Yes.
Understand? The reference is fixed. Understand? So therefore, with respect to that particle, I see that particle is moving like this. Right?
Okay.
So see, in general, if you take a body and if you see every particle in the body, and if you take any other particle in the body, you will always find that some particle is rotating with respect to some other particle.
Yes.
Not only this. If I take this particle also, if I take this point and this point, okay, if I take this point and this point, that is this point and this point.
Yes.
So this particle is rotated.
Yes.
So you see, only thing is the distance between the two particles will not change. That will be fixed.
Yes. Yes.
Okay, because it is a rigid body.
Yes, sir.
because it is a rigid body. But the motion of each one of them can be considered to be, it is moving with respect to each other.
Yes, sir.
Fine? Anyway, fine, good. See, you have got a very keen eye. I wanted to avoid that and take it up later on, but your eyes are very sharp. Right. Now, angular displacement of a particle constituting a rigid body in fixed axis rotation, pure rotation. So here you see P, A, B, I think all this. So let A, P, A dash. What is this? A, P, A dash. Okay, B, D theta 1, let B, P, B dash. B, P, B dash, B, D theta 2. So A, P, A dash is equal to A, P, B plus B, P, A dash. And B, P, B dash and is equal to B, P, A dash plus this one. Okay, so but angle APB is equal to angle since the body is rigid. So therefore, hence APB is equal to D theta 1 is equal to D theta 2. That means now, if A has moved from A to A dash and it has made some angle D theta 1, B has moved from B to B dash, it will also make the same angle.
Yes, sir.
So D theta 1 is equal to D theta 2. And therefore, angular velocity is also same, angular acceleration is also same. This is the way of proving that that the angular quantities will be same for all the particles in rotation motion.
Yes. Yes.
Because if they ask you to prove, you should be able to prove it, right? Okay, now take this case here. Okay. So here, consider the situations given below. Okay. So P1, P2, P3, P4 are the free pins. Free pins means they can move. Free means it is constrained, but it can move. See, only this point is rigidly secure. Describe the motion of the rectangular frames in the two cases. So here, in this figure, from this to this, what type of motion is the frame doing here? Curvilinear translation. In this case,
Yes, sir. Rotation. Rotation and rotation.
yes, only rotation. Because from this if you draw any line that is doing this. So not curvilinear. Who said that curvilinear rotation? Don't say all that. Okay. See, curvilinear translation. That's it. There is no curvilinear rotation. See, if there is curvilinear motion or translatory motion, pure translatory motion, if you have fixed the reference, if you have fixed this reference and if you say a body moving, that means with respect to this point, the body has rotated. Hello?
Yes, sir.
Yes.
See, I am standing here. Okay, now today Swaroop is here. Swaroop moves like this. Okay, so with respect to me, Swaroop has rotated.
Yes.
Because the line joining B and Swaroop, it is changing the angle. So it is rotational motion with respect to this point. Okay, but now Swaroop is moving. My reference point also is moving with the same velocity as Swaroop is moving. Then Swaroop is at rest with respect to me.
Yes, sir.
Yes.
Okay, so this is the case of rotational motion.
So I didn't understand how the rotation.
See, now from this point you draw any line, man. See, you have to abstract like this. See, why did you say this body is rotating? You have drawn a line here. You are drawing a line here. PA, no. This line PA is making an angle.
Yes, yes.
If you take PA as a reference, then if the body has rotated, this PA has made an angle, PA dash has made an angle.
Yes, sir.
Any arbitrary line makes an angle, so it is having angular displacement. So we say it is rotating. So see, come on, apply the same thing here. Okay, apply the same thing here. So you draw one line here. From this point you draw one line here. And now that line is now here. It has changed the angle.
Yes, sir.
Or why you want to draw any line? You can take this frame. This line you can take. This line is perpendicular to this line. Now it is making an angle. Any line now, see any of these rectangular lines which is forming rectangular, is changing its angle. So therefore it is rotating. I am rotating about a fixed point.
Fixed point, yes, sir.
So therefore it is pure rotation. See, the body is purely rotating, man. If you now don't go to particle dynamics, each particle in the frame is moving. Okay, it is also rotating and translating.
Yes, sir.
But as a body as a whole is rotating.
Yes, sir.
Okay, fixed axis, pure rotation. Now one more concept here. Yesterday, because you are all very eager to use center of mass. Allah, I see some of you. Why user Kumbal ka kala yadi help Divanthali yesterday. Fixed axis rotation may be centroidal or non-centroidal. So if you take this disc and if this is the center, if the center of that or the center of mass of that, and if it is rotating, then it is called the centroidal rotation, where P is the axis passing through the center of mass of the rigid body. We call it a centroidal rotation.
Yes, sir.
Non-centroidal rotation. When point P peaks through any other point of rigid body, we call it a non-centroidal. You can see this diagram is very clear. Okay? Hello?
Yes, sir.
Now combined motion. In this type of motion, the linear and angular velocities of different points of rigid body will be different relative to fixed point. In other words, the 2 points of rigid body undergoing combination. That is rolling motion. Rolling motion. Forget it. I have already explained this. Okay? Now this is precisely combined motion is what I was showing you the other day.
Yes.
So this is the combined motion. So you can see that this whole body is translating. The velocity vector is like this, and it is also rotating. So it is combination of both of them. That is precisely what I have to tell you. Okay?
Yes.
Now, if you still want to read something, you can read quickly. So this is a rotation about an axis. Translation equals broad category of motions. Rolling is an example of the kind of motion. A rod lying on a table, when it is pushed from one end of its perpendicular direction, also executes the kind of motion. To understand, let's know a few more examples. That is, you keep a rod on a table and you hit it. So the rod will move and also it will rotate. Supposing you hit it perpendicular to the rod.
Perpendicular means
Hingo, idu rod andirko, idu rod. If I push like this, then it is only translatory motion.
that's perpendicular.
Hey, this is translatory motion. Now you said that I am hitting it along the axis. See this force. See, I have already explained this, man. The force, the line of action is passing through the center of mass. So this will only translate. Okay. Now if I do like this, again it is translating. But now if my finger is perpendicular to this, see here. Now what happened? This moved and also rotated. Okay. That's what is it. A rod lying on a table, when pushed from its one end in its perpendicular direction. Okay, will also execute this type of motion. Now this rolling also I have explained. Okay, the rotation of the wheel from frame rotation is also fixed. So the rotation of the wheel from this frame, which frame? That is, you have taken this point as the reference point. If you take the center of the circle as the reference point, okay, so with this as the center and this becomes the frame of reference, moving a vehicle appears to be rotating about its stationary axis. That means now, supposing this axle, if you are sitting on the axle, okay, then you will only sense the wheel is rotating around you.
Yes.
The rotation of the wheel from this position is rotation about the fixed axis. Relative to the frame fixed with respect to ground, the wheel appears to be rotating about the moving axle. Therefore, the rolling of a wheel is superposition of both two simultaneous but distinct motions: rotation about the axis fixed and the wheel, and translation of the axle together with it.
Yes.
That is, if you take any reference outside this wheel, supposing you are standing here, right?
Yes.
If you are standing here, then you will see that the wheel is rotating also and moving also. Just like how the shuttlecock is moving. So it is a combination of both. That is what is told. Now, again, some important observations here. Every particle of the body always remains in the plane perpendicular to rotation. Therefore, this kind of motion is known as general plane motion. every particle of the body always remains in the plane perpendicular to the rotational axis, and therefore this kind of motion is also called as general plane motion. That plane is in motion, plane of rotation, to general plane motion. Relative to every particle, another particle in the plane perpendicular to the axis of rotation moves in circular path. The radius of circular paths equals the distance between the particles, and angular velocity are equal to this. Already this part has been discussed.
Yes, sir.
Yes.
Rotation about the axis in translation is superposition of this is important. Rotation about the axis in the translation.
Yes, sir.
See.
Yes, sir.
Yes, sir. Yes, sir. Your friends also should say yes, sir. They are not saying yes, sir. They are done good. Okay. So, see now, the axis is perpendicular to this wheel. Axis is perpendicular to this wheel. Okay. And as the wheel is moving, see now the wheel is here at time t1, at time t2 the wheel is here. Okay. Now what has moved? This axle has moved from here to here. So axle has moved, that means every point has moved.
Yes, sir.
So there is translation. At the same time, about this axis, it is also rotating. So it is
Yes.
combination of both. Now, if the person is sitting here inside, okay, fixed on the axis, then he will see only that the wheel is rotating. He will not sense the translatory motion.
Yes, sir.
Yes, sir.
But if the person is here, okay, so he will see both. It is translating as well as it is rotating.
Yes, sir.
So he will see both the vectors, that is rotation as well as this.
Yes, sir.
Okay, fine. Now, another name for this is constraint motion. Now, rolling of a body, motion of a bar in a vertical plane are action under the action of gravity and reaction constraints are suitable example of constraint combination motion. So,
Yes, sir.
so you can see here that there is a friction between the, there is what? This body is rolling. Hello, this body is rolling.
Yes, sir.
And there is friction.
Yes, sir.
But remember, while I say it is rolling without slipping.
Yes, sir.
Rolling without slipping. Rolling without slipping.
Yes, sir. Yes, sir.
Then this friction is static.
Static, yes.
So this friction is only to support. You see, if my hand wants to rotate, so I will use this hand as a support and I will roll.
Yes, sir.
Got
Yes,
it?
yes.
I'll use it as a support and roll. But if there is no friction, between this and this wheel is rotating here only.
Yes, sir.
In rainy season, see, when the road is very slushy, the car and the wheels and all will get stuck in the mud. You have seen that?
Yes, sir.
Wheel is rotating, but the car is not moving.
Yes, sir. Yes, sir.
So therefore it is slipping. The wheel is slipping.
Yeah.
Now if the car is smoothly going, then we say the car is moving without slipping.
Yes, sir.
Now if I say this wheel is rotating as the wheel is rolling without slipping, then any one mathematical condition you say which will prove that the wheel is rolling on this road without slipping. The radius of this wheel is R. And this is at position A and this is position B.
AB is 2 pi r.
Yes, do it. So if AB is equal to 2 pi r,
Yes, sir.
then we say it is rolled without slipping.
Yes, sir.
Understood? Understood. So this particle which was here at some time will now keep moving, and then again this particle when it comes here, this would have gone through 2 pi r distance, and this should be the distance.
Yes, sir.
So here there is friction, but this friction is static friction.
Static friction. Okay, yes, sir.
Now if there is slippage,
Yes, sir.
then the friction, that means now this will slip. That is, there is relative motion between this and this.
Yes, sir. Done.
then it is dynamic friction. So the friction coefficient there, if at all you have to use, it becomes kinetic friction.
Yes, sir.
But not rolling friction.
But not rolling friction.
Rolling friction is different.
Yes, sir.
Don't confuse that with this. Clear?
Sir, when rolling friction actually.
Supposing there is a stone here.
Stone here, yes, sir.
There is a stone here.
Ash time.
Okay. There is a stone here. Then this wheel is trying to go over the stone. Then this stone will give the normal reaction.
Yes.
Normal action is.
And this normal reaction, if you see, it will create a torque to impede this motion.
Yes, sir.
Yes.
And therefore,
Yes.
therefore it will decrease. So it depends upon the deformation of the wheel.
Yes, sir.
Now that is not there for a syllabus, please don't ask. But only know that rolling friction will come into picture if the wheel gets deformed.
Yes.
Yes, I have already explained this long back. Now you see, a ladder is lying on the wall and this ladder is slipping on its own. Hello, are you with me?
Yes, sir.
Yes.
Now you see here, so it is constrained by the walls.
Yes, sir.
It is constrained by the walls. If the walls was not there, if I keep the ladder like this and leave my hand, this ladder will fall down like this.
Yes, sir.
But since it is constrained, it is going to slip. And what you have to notice is that, so here you see this ladder will rotate about some point.
Yes, sir.
Because, so you remember, I have drawn an arbitrary line along the ladder. And the ladder is falling. See, the ladder is falling, what happens? See, if my hand is the ladder, assume that there is my hand is going like this. The ladder is falling like this.
Yes, sir. Yes, sir.
So if you see this point, of the ladder, it is translating, it is moving to the right, and at the same time the angle is changing.
Yes,
Yes.
Yes, sir.
So this is a typical case of translatory motion as well as rotation. Is it clear to all of you? So rotational motion doesn't mean only wheel and roller. Okay, so you see, that's what I'm saying. It's the concept. So rolling is a concept. Okay, rolling is a concept. So here also you can use the same concept here and say, well, there is the rolling concept. Rolling is a concept where it is combination of both rotational as well as translative motion. This motion under constraint here is also a combination of rotation and translation.
Yes, sir.
Yes, sir.
Got it, all of you?
Yes, sir.
Yes.
Yes, sir.
And we'll analyze this. Okay? Okay? We'll analyze this. This is a typical case where rotation of this. So now you see here. This is a top which is spinning. You can see a top is spinning here. All of you can see?
Yes, sir.
So this dotted line is the axis of the top. This dotted line.
Yes, sir. Yes, sir.
Yes, sir.
So the particles of the top are rotating about this axis.
Yes, sir.
Yes, sir.
Yes.
And this axis itself is rotating about another axis.
Yes, sir. Yes.
I hope all of you captured it.
Yes, sir.
Yes.
So therefore it is rotation about the central axis plus the axis itself is rotating and one point of this axis fixed.
Yes, sir.
So this is called precession of the central axis.
Yes, sir. Yes.
Ah.
Yes.
Okay, so this is a typical thing. Okay, and we need to analyze this also. Anyways, so you are more interested to read everything more. Please read. This kind of motion, the body rotates about an axis that also rotates about some other axis. Analysis of rotation about rotating axis is not the scope of JEE. Therefore, we will not discuss to have an elementary idea. It is only to have an elementary idea. Some many things will happen like this. An example, considering a rotating top, the top rotates about the central axis of symmetry and axis sweeps the core about the vertical axis.
Yes, sir.
The central axis continually changes orientation, so this sweep is called precession. Another example of rotation about the axis is rotation of the table fan swimming with rotating. The table fan rotates the horizontal shaft along with this table fan is spinning and going like this.
Yes, sir. Yes.
Okay.
Yes, sir. Yes, sir.
Now, this one more set of equations which are all familiar, angular displacement and all. These quantity are similar this one. So theta is equal to theta naught plus omega t.
Yes, sir.
You remember all this? V is equal to V
Yes,
naught
sir.
plus.
Alpha 80. So V is equal to V naught plus 80.
What is this equation? Theta is equal to theta naught plus
Sir,
omega naught.
acceleration is
Hey! This is displacement. X is equal to x naught plus vt. Hey! X is equal to x naught plus vt.
angular displacement.
So for that is for linear.
Yes, sir.
Similarly, we got angular displacement equation.
Displacement.
Yes, sir.
Yes, sir.
Yes, sir.
Understand? So the particle is moving with velocity v. If I say velocity v, not this equation, then you say what is the displacement of the particle? Initial displacement plus the displacement in the time interval t.
So, this velocity.
Now it is angular displacement.
Yes, sir.
Theta is equal to theta naught, initial displacement. That is the displacement at time t is equal to 0, and it is moving with angular speed omega or angular velocity omega, and therefore it is theta is equal to theta naught plus omega. Okay?
Yes, sir.
When can we write equation like this?
Zero angular acceleration. Like when it is constant.
Louder,
There is no angular acceleration.
better. When
And-
can we write this
and
equation?
when that omega
Small
angular velocity
acceleration.
versus like when it's constant.
When omega is also constant. Constant means you know
Percentage.
its angular speed is same and direction is also same.
And
Yes, sir.
yes.
Then similarly we used to write v is equal to u plus at. And now we have got omega is equal to omega naught plus alpha t. All this we have discussed.
Yes,
When can you write this equation?
uniform angular acceleration.
When alpha is uniform constant.
Badile,
Uniform.
when alpha is constant.
Constant acceleration. Yes, sir.
When alpha is constant.
Constant acceleration.
Yes, sir.
Remember constant, that means its direction and magnitude must be same. And we used to write here s is equal to okay, you remember this?
Yes, sir.
Huh? So theta naught omega naught half alpha t square.
Yes.
And this other form you see most of the books don't highlight this. So it is theta naught into half omega naught plus omega t. See, please appreciate this.
Yes.
What is this half omega naught plus omega? The initial velocity means initial angular velocity at time t is equal to 0
Answer.
plus the velocity at the time t, which we call it as final.
Answer.
And the average of this into t is also another form of this equation.
Average velocity.
Yes, sir.
So average velocity into time,
Yes.
Yes, sir.
provided
Alpha
constant acceleration is constant.
Constant acceleration.
Yes,
Then
sir.
v square is equal to u square plus 2as. So here it is omega square omega naught plus 2 alpha into theta minus theta.